Right guys, welcome to the class. Let me know if you have any questions before I start the lecture. Okay, so if you don't have any questions, then please pay attention. This is an extremely interesting topic, okay? Concept wise as well as implementation wise, and probably I mentioned that this is a data structure which is very often used as a problem in your interview questions as well. Trying to locate my pen. Here it is. Okay, so I hope that you people have got some understanding of the binary tree data structure, and here we are looking at one special kind of binary tree which we will call as binary search tree, because the tree has a property which helps us in efficient search of an element, right? So that should be evident very soon. So let me go through these points that I have over here. We will learn and ultimately implement this interesting class of binary tree which is called binary search tree, or BST in short. Alright, so what is the interesting property of this tree? It is binary, and all the nodes in the left tree or left subtree are less than the root, and all the nodes on the right subtree are greater than the root, right? So that is a very important property of this class of binary tree. Okay, so you will have a root, and then we know that, right? Basic property of a tree has sets of nodes. One of the node is designated as the root, and once we pick a root, then we can think of left subtree and right subtree, right? And this is a recursive definition, if you remember. So the same binary tree with an added property which goes like, the nodes on the left subtree, they should be less than the root node, and all the nodes on the right subtree, they are greater than the root node, and this applies recursively. All right, so yeah, so the last point which says that the subtree that you'll have in binary search tree are also going to be binary search trees. Okay, so now let's with this information, the information that I gave you, let's see if we could make some progress towards the implementation, right? So fine, here goes the first line of the class definition for this class of data structure or abstract data type that you may call it, which we are calling as binary search tree. Okay, now tell me what data fields we would need for this tree. Okay, yeah, need a root. You all agree with me? Is there anything else that we need? I mean, in terms of data fields, right, we would need a lot of methods, right? But in terms of data fields, do I need anything else, right? In the linked list implementation, what were the data fields for the linked list implementation, if you could recollect? Yep. For linked list, not the int node, right? Yep. Head, tail, and cursor. Yeah, got it, right? Similarly, see, that's what I'll say. Whenever you are learning about it for the first time, when you're preparing for the exam, right? Let's worry about exams. Put all these things next to each other, right? You don't have to formally do it, just at least keep that here, okay? So in this data structure, we just need a root, right? You agree with me? That's the only data field we need, right? And look at this data field, which is, we will call it root, and its type is BT node type, which we learned, right? So this is the basic node which will help us in creating this beautiful structure of binary search tree, right? And in the BT node, if you remember, we have these three data fields for data, for left reference and the right reference, right? So yeah, we need to remember what we learned in the previous class, right? Okay, so that's the data field. Now we need to think about the methods, and they are going to be really interesting methods. So let's start with the first method, which is the constructor method. What should I do in the constructor? If you create a binary search tree, do we expect any parameter? Is it an arg constructor, no arg constructor? Do we need any argument? So as I was saying, these are all very similar. So when you created the linked list was empty, right? When you created a stack was empty. When we created a linked list, it was empty. Later on, we went on to insert the nodes in those data structures. Going by the same principle, we will keep the binary search tree empty, and here you go. Simple constructor, root is being initialized to null. Questions? Simple, okay? Then we can think of other very simple methods, like checking whether the tree is empty or not. I'll leave that on you people to figure out, but probably we have the implementation, extremely simple one-line implementation. Just check root. Is root referring to null or otherwise? If the root is referring to null, then that means we just invoke the constructor. We did not add anything to the to this binary search tree. Okay, fine. What should be the next method that you can think of? Created the tree which is empty, right? Written a method which will check whether it is empty or not. What should we do next? Create it, right? I mean, don't be surprised if, okay, yeah, I was assuming we will create, but that's okay. Ultimately we'll create it. We will insert the nodes, right? And that's how we will create the binary search tree. But before that, let's look into this very simple method, which is in order method, right? Now let me ask you this question. In the BT node, did we implement in order traversal? Remember something? Yeah, we did. This is not the first time when we are defining in order. Okay, but this time this in order traversal is important, because we will say, okay, fine, start the in order traversal from this node, right? Where from we start the in order traversal? From the root itself, right? We need to tell from where we have to start. So in this in order traversal, what should we do first? Yes, go ahead. Sorry? Yeah, you should check, right? If the root is empty, then we don't need to do it. If the root is not empty, then what we do? Sorry? Okay. This is it. That's why I was saying, right, guys, it's not possible, right? Unless you are too studious, I don't expect that you'll remember everything from the previous lecture. But something, if you remember, right, it will help. But anyway, I'll help you out. Look at it. We just need to invoke the in order traversal on the root node. And what is root node? Root node is anyway an object of a class BT node, and on which we had defined in order traversal. Remember that? In order traversal has already been defined on the BT node, right? In the previous class, when I explained, when we were learning about the simple binary tree, then we started with the structure of a class BT node, right? And there we had data left, right, and there only we kind of came up with the three methods for in order traversal, pre-order traversal, and post-order traversal, right? So here we just need to pick that interesting node, which is our root node, and invoke this in order. It has been defined on that node, right? From that node itself, it will start, recursively traversing the tree in order manner, right? Yeah.
Is referring to an in-order method made in the node class.
Yes.
And this is in the binary search tree class.
Yes, this method is in binary search tree. Next question. Yep.
Wait, what
Okay, okay. In order to what in order does, right? Interesting question. Let's think of a tree. And you know, I was in a different state of mind in the last class, too confident, right? Expecting that students know everything that I'm going to teach. But anyway, let's make a simple tree. A, B, C, D, E, and F. Let's make it slightly complex. All right? I forgot who asked this question. You asked it, right? Yeah. So, guys, I mean, again, right? I'm sorry about this thing. You have been reaching out to me, and I'm trying my best to implement. Okay. I was lucky to find this implementation from the last year, and I did run that before I came to the class. Implement, that's when you really learn about it, and you need to think about it, right? Probably while I'm teaching, you'll say, okay, fine, I got 70%, but that 70% is not important. It should be 100%, right? Anyway, so when you have created a tree, right? I told you, I mean, in the earlier class also, how will you check whether you really created a tree? You'll have to print it out, right? You will have to traverse through it. So there are three options available for traversal. The pre-order, should I explain pre-order? Or pre-order is fine, right? The in-order is slightly tricky where recursively what we do, recursive left subtree in order traversal. Sorry? It prints that. It will print, right? What is the purpose of traversal? Visiting every node and doing something, right? So in the basic version, we'll print it out. But in more interesting kind of questions that I might ask in the exam, you may inherently use traversal, right? Is that thing clear? If those were if these nodes were numbers, right, I can replace it with numbers, right? And I say, okay, fine, add all the numbers that we have in the node of the trees. You'll have to traverse, right? Any traversal you use, in order, pre-order, post-order, we need to visit these nodes and add them up, right? So in order traversal, as you asked, recursively left subtree, in order traversal. Then in the second step, print node, visit node or print root. Print or visit root, same thing, right? And after that, in the third stage, recursive in order traversal of right subtree, this guy. All right, so first you will do this in order, then this one, and then this in order, right? So this in order would be simplest, DBE. We are done with this, right? Recursively DBE. Then this guy over here. Now recursive of this one in order. There's nothing here, so pick C. Here there's nothing here, GF. Got it? I might be wrong, right? Correct me if that is the case. This is kind of puzzle only, very simple puzzle. In order traversal, pre-order traversal, and post-order traversal. Okay, fine. Now my question to you is true and false question, right? I'll say this is a recursive method. True or false? It's recursive, right? You all are with me, right? This is recursive. This is not recursive. Pay attention. This is not recursive because what? We are not calling this method itself. We are calling, or we are invoking the in-order traversal which we have implemented in the BT node. right? B tree node. It's making sense, right? So please, guys, this is, yep.
Is this overriding the BT node method?
Another question. Thanks, you gave me another question for exam. We are overriding, true or false? Yep. You have to do what? Implement? Sure, implement. You are learning Java also, that's the reason I'm grilling you more. Inheritance. Overriding only happens in inheritance. We are not inheriting, right? Are we inheriting? No. For inheritance, we use the keyword extends, right? And that is a totally different problem. Here, for this data structure, which is the binary search tree, we are using that node, BT node, as a class to define its data field, which is root, right? Yeah, so it's not no overloading and no overriding. This is just invoking a method that already exists, not even overriding, sorry, overloading. Got it? It so happens that these two methods are given same name, and they should be given the same name because these methods are doing the same stuff, right? Yep. You can, that's your method, right? You can do it. That's your method, you can do it, but I'm fine with this kind of notation, right? When you implement, you can give a different name to it. That's totally fine, perfectly all right. Okay, good. So this is a call to in order from the BT node class, so it is not recursive call here, and that method is in fact recursive in nature. All right, good. So very simple method, but yeah, interesting. We did not implement in order traversal for, sorry, pre-order and post-order for this one, but I'll assume that you can do it, right? So simple one-liner thing. Practice all those things, okay? Now let's get to interesting exercise, guys. I'm very happy to know that some of the students who had no background in Java, were just learning Java, were able to do very, very well in the midterm. So that emphasizes 2 points. Either they are very hardworking, they are also picking up Java, or the data structure that we are learning is not so dependent on Java, right? Concepts. So this question that we have here is all conceptual question. Okay, so what we will do now, you will be given some data, right? And we will create a binary search tree. Okay, so here's the data coming. We'll scan the data from left hand side, right? So that means the first element or the first node that we need to insert into the binary search tree is which one? 45. So make 45 the root. All right, we are done with 45. Now the next element is 21. So when you're creating this binary search tree, where would you like to put 21? Should we change the root? No, right? Why to change the root? We have 45, just leave it as 45. Now we will adjust 21. Where should I take 21? On the left or on the right? Yep. On the left, right? Because we are making a binary search tree. Whenever we are inserting a node to the tree, we want to make sure that it remains binary search tree. Very simple question. I will ask, right? I can't manufacture questions. I'll ask question, and this will be probably simplest question. So here goes 21. What's the next element? 39. Where should I put 39? On the right of 45? Yeah? No, I can't, because whatever we have on the right hand side should be greater than 45. So it will go to the left of 45, which is 21. But here again, I need to decide, right? 21 is already there. I need to make a decision. Like, sorry? To where? To the right of 21. You all see that, right? We will have to search, 45 was already a binary search tree. You agree with me? Just node 45 is already a binary search tree with no left subtree, no right subtree. Okay? So when we had to add 21, we figured out that it is less than 45. We put that on the left hand side. Now you got 39. So everything has to be very systematic. You start the search from the root. All right. So from the root, you compared 39. You figured out that 39 is less than 45. So you went to the left hand side. And the left hand side, you found that there is a node 21. If there was nothing on the left hand side, you will find you'll just put 39 over there. Right? But there is a node 21 on the left hand side of 45. So now we need to compare, right, with respect to 21. And since 39 is greater than 21, so it should go to the right hand side of 39. Is it a binary search tree? Yeah. It is a binary search tree, right? So why? This is the left subtree, right? Is it binary search tree? Yes, it is a binary search tree, right? There's nothing on the left hand side. That's okay. But what we have on the right hand side is greater than 21. So recursively, our left subtree is binary search tree, and this whole is also binary search tree, because if you compare all the nodes in the left hand side of this tree, they are less than 45. Okay. Now we will add 83. Where should 83 go? Compare with 45, should go to the right. Fine. So since there was nothing on the right hand side of 45, so we could plug it over there. Good. Now after 83, we have the next node, which is 62. You compare 62 with 45. It is on the right hand side. You will come here. Now we already have a node over there, which is 83. Right? So we'll have to plug it somewhere on the left or the right of 83, and for that we will compare 62 with 83, and 62 is less than 83, so it goes on the left hand side. Got it? Is it a binary search tree? It's still binary search tree, right? So we are inserting in such a way that the property is still holding for that binary search tree. We are done with 62. Now 96. Do the same thing, compare it with the root first, which is 45. It's greater than 45, you come here. It's greater than 83, and luckily we don't have anything on the right hand side of 83, right? So 96. Good. Now we have the last element left, which is 11. And where should the 11 go? Done. Right? Now look at this binary search tree. Yeah. Now we have the right subtree also, which is over here, and this right subtree is also a binary search tree. Right? 62 is less than 83, 96 is greater than 83. Can someone tell me something interesting that we can observe here in this tree? Something very interesting. Yes.
The largest value is all the way to the right on the bottom level, and most values always end up on the bottom level.
Very good. Right. So I'll give you 100% for this, but I'll reformulate that the leftmost node is the smallest. Which is the leftmost? 11. All right. And rightmost node is the largest. Okay. And here goes the assignment. Assignment could be a question in exam also, right? I can't be more explicit than that. Can you write a method that finds this largest element or the smallest element in a binary search tree? That will be recursive. It should be recursive, right? Just think about it, right? Yeah, get ready. I mean, what I'll do, so some of you are asking for practice questions. I'll just put that as a practice question. If I forget, then please take a note of it. Question? Yep.
Is 45 arbitrary? Like you just pick the first number at the beginning to make the root?
Very good question. Whichever number is the first will become a root. And if I, how about it? An exercise. Do it, right? This is your note. Let's create a binary search tree starting from 11. Right? From right hand side to left hand side. What will be the root then? If you start from 11, what will be the root? 11. right? If 11 would be the root, then 97 on the right hand side of 11, 62, you can add just 83, right? So the very first node you start with will become a root. Okay? So yeah.
Is there any reason why, like after 39, 83 couldn't be like a right node for that? Like you treat 39 as another root and then have 83 as its right node?
Okay, you know, we did in this order. The first one was 45, then the second one was 21, and when 45 is already there, 21 can go only on the left of 45, right? Then we got 39. Now 39, when you want to add 39 to this tree, you will compare it with the value that you have in the root. It is less than 45, so it will come to the left hand side, right? So in fact, the insertion of a node in a binary search tree also involves search. You agree with me? We are searching, right? We are searching to find the perfect place to put this node, right? So I did not put 39 anywhere arbitrarily. I started searching for the correct place where I could hook it in. Did I answer your question?
But I kind of meant that, then why did 83 have to be the child of 45? Couldn't it have been the child of 39?
Why 83? No. See, when you wanted to add 83, we already had 45, we had 21, and we had 39, right? So these nodes were already there. Let me create it for you. 45, 21, and we had 39. That was the tree that already existed. Now we want to add 83. So when you're adding 83, you will start the search from the root, right? So you will compare. 83 is more than 45, so you can't go on the left hand side. You have to put it on the right hand side of 45 because it is greater than 45, right? It is greater than 45, so it should be on the right hand side of 45. Now your question is, if you put it here, right? If you put it here, then this is violating the binary search tree requirement. Why? Because you know, here we are fine, here we are fine, but we are not fine here. All the nodes which are on the left hand side of the root, which is 45, they should be less than 45, but 83 is greater than 45. Okay, right? So we need to religiously follow these rules. Yep.
Whenever we're adding a new number, we always start with the root.
Yeah, very good. Yeah, pretty much, right? Yes, we always start from the root, and as I said, that this insertion involves search as well. You search, find the correct location, plug it in. Very good question. What if two numbers are equal in binary search tree? And the answer is something you will not expect. We are not allowed duplicate numbers in binary search tree. Okay, you cannot. Binary search tree should have unique values only. Now question arises, if for some application you want to allow duplicate values, then I'll say maybe use one more data field which will keep account of how many times you have seen this number. That's what I am thinking about, right? I should have done this homework, but while I was preparing, I thought, okay, fine, this is how I'll do. Okay, duplicates not allowed. Any other question? How about this one? We have another exercise, right? So what should be the root? The same order we are scanning from left hand side to right hand side, right? 62 should be our root, all right? And then 96, where will 96 go, left or right? Right. Guys, if this is a question and I'm a student, I don't want to lose even a single point. If the professor is giving me such a simple example for 5 points, I'll meticulously write every step, not wasting time, but using pencil steps. I'll see like what is being asked in the exam. Read the questions carefully. That's the first message, right? Some of you did not read the question carefully and you gave the correct answer to the incorrect problem, right? So make sure that your answer is compatible to what we are asking. Okay, so show all these things. Then 11, where should 11 go? To the left hand side of 62. Where should 39 go? Traverse all these things, right? Well, for this 39 that we want to put, we will start with the root. You compare 39 with 62. It is less than 62, so we can't put it here. So since it's left already has a node which is 11, so we'll have to now compare 39 with 11. Put 39 here. All right. Good. Then 21 in the same way, right? Then 83, then 45. Okay. What we have now is more interesting, right? Where I would expect you all to implement, and I'm not asking you to do some very big project. Just take these codes, put it there in the classes and fill in the blanks. You'll have to probably write some very simple code. So we will now attempt to write this method for inserting a node in the binary search tree, and that's how we will create the binary search tree. Okay, so this is the method called insert item, right? If when we are adding those numbers, somebody gave us those numbers, right? So we do need this item. And guys, I mean, you need to be very focused on these codes, right? Otherwise you'll miss it. So since the information has been given to us, we need to put that in our binary search tree. We will have to first create a node, right? So this value that you have would ultimately go inside this new node that you created, and it should be of BT node type. Okay, what do we do next? Now we need one more. We need a temporary pointer, I would say, which we will use to keep a trace. We will have to trace through the tree, right? We have done that on that piece of paper, I would say. Rather, we know how to do it conceptually, right? Now we are thinking about its implementation, and in implementation we must have a temporary variable cursor. Here we will define our own cursor, because it's not like linked list where we already had cursor, right? So let's define cursor, and we will make use of this cursor to trace through the tree in search of the perfect position to plug this item in, right? And one more interesting thing, we have a Boolean variable done. Guys, it's possible that you can write your own version of this method which may still be correct, right? So how to make sure that what you are writing is correct? Write it down and check whether it works or not. If you don't do that, then you'll be forced to understand what we have on the slide, which is a good code, which is optimal, pretty good, right? So the reason why I'm suggesting you to write your own version, because probably you will not use this done Boolean variable, right? But we are using it. You'll find that it is very convenient to use it. So Boolean done is equal to false, right? We are starting with that. Then now let's look at all the possibilities. So the first thing that you would like to check is root null? If root is null, then yeah, very simple. We will create this node and we'll make it the root, right? Done. If root is equal to null, then let's create this new node with the item information that we are getting as the parameter, and set the root as new node and return. Else, if that is not the case, now you need to search. Okay, so here we go. For searching, we will make use of cursor. We will set the cursor to root, and now we will start the while loop, and this while loop will search for the appropriate position, and here we are making use of the Boolean variable done. While not done, if now we'll check for the condition. If item that we want to insert is less than the cursor data, then what to do? If it is less, then what? Let's map that thing to the implementation, right? What will you do? Sorry? Cursor? So how will we do that? You are saying if it is less, then we will move on the left hand side, right? How to map that into implementation? Whether left is null, yeah. If the left is null, then we are done, right? We can plug it in there, very good, right? It is less than that thing, and we should check if fine it is less than root, but do we have anything there? If we don't have anything there, then we are done. Let's plug it in there, right? Good. So yeah, exactly what he mentioned. If its left is null, then that means we have nothing in there, so we can simply plug it in there. How? We'll simply say okay, so first create it, because we did not create outside, right? We'll again create it for this case, new node, and then cursor dot set left new node, and done is equal to true, right? Else, if it is not less than now you would if it is not less than the current node, then it must be greater than that, right? If that is the case, you will do cursor is equal to cursor dot get left. Guys, I think I missed a very important information over here. We are checking this thing, right? If wait a second, this is nested if. This is nested if item is less than cursor dot data. If we have a space there, then let's plug it in. We may already have another node. If that is the case, then we need to update the cursor. Let's move to this point and then we will search, right? Something like this. You have 45, 26, 50, right? And we want to add 33 as an example, right? So from here, when you compared, you figured out it is less than this, right? But we have another node here, right? So yeah, that's what we have to check. If there is something on the left hand side, then if it is not null, then we need to go to that. That's what we are doing here. Update the cursor. Cursor is equal to cursor dot get left. Keep going left. Why? Because our item is less than the node. Therefore, we are going left. And there again, we need to check. Should we further keep going on the left? If this was 35, if this was 35, you want to add 33. From here, you came here. But now again, you will check. So initially, your cursor was over here, right? You compared, this is less than that, you came here, we already had a node, so we could not add the node. Now we need to decide 33 goes to the left or goes to the right, right? For that, first we need to update the cursor. Cursor should be equal to cursor dot get left, right? I'm pretty sure you need a lot of practice. Okay, fine, doing good. So this is when it was left less than the data. The other possibility is if item is greater than cursor dot get data. All right, if that is the case, then what we do? The same sequence, right? The same logical sequence. You will check whether we have something here or not. If this was 50 and there was nothing here, right? So what will you do? How will we know that there is nothing there? Check the condition whether its right is null or not. So this is kind of symmetric in concept, right? It's symmetric if cursor dot get right is equal to null. That's the case, then what we will do? We'll create the new node and simply we will set cursor dot set right is new node. Done. Otherwise, we will go down, right? We'll move to the right by setting cursor is equal to cursor dot. Oh, sorry, that will be the outside this. You are done, so you should set up done is equal to true. Otherwise, if you are not done, there was no space, you need to further traverse on the right hand side. All right. Questions? Else? Done is equal to true. What is the third else part? There are three possibilities, right? First possibility, if the item is less than cursor dot get data. The second possibility, if item is greater than cursor dot get data. What's the third possibility? Yeah. Yeah, if the item is equal to that. So what do? Done is equal to true. What does it mean? Don't do anything, right? We cannot add duplicate. Got it? So that is the why. Why? It means that we got the duplicate item which we don't want to add. Questions? Practice. Okay, make sure that you can do on the numbers, and then maybe look at the code, understand the code, try to write the code yourself without looking at it, making sure that the implementation and the concepts are on track. Right? In exams you're fine if you miss here and there a little bit, partial grading is there, partial credit is there, but for homeworks it is tricky, right? For homework it should be correct, it must run. Yeah.
Can we implement this method like recursively?
You can we, I think yes, somebody attempted to do it. You can, but you need to figure it out, right? Probably you may, right? But might be difficult, right? Recursively it's not coming to me as I'm teaching. If you could do it, show me, I'll be impressed, right? So guys, these extra things that you're doing, I should know that you're doing something extra to deserve the extra credit. Okay? Should be possible. And while and done. So now let's do the traversal, okay? And here we go. You want to do some practice? Somebody please tell me what is the pre-order traversal of this tree? What values do we get in what order? Next few minutes we can use as a recitation, okay? In pre-order, what's the first node? 45. Then, sorry? 21. Then, sorry? 11. 39. 83. 62. 96. Let's do the post order traversal. Yeah. What is it? 11. Then post order. 11 then 39, right? Left subtree, right subtree, then root. 11, 39, 21, 45? No, root comes towards the end, right? 62, 96, 83, 45. In order traversal. Eleven, 21, 39, 45, 62, 83. Which traversal is meaningful here? Sorry? Yeah. In order traversal. Why? It sorted the data. This is tree sort. Right? What is tree sort? Slightly complex, but what we do in tree sorting is when the data is given to us, we create the binary search tree from that data. Okay, and then we do in order traversal, which will give us that sorted data. Could be a question. Please practice that. Take any random data, right, in any order, create a binary search tree, and on that binary search tree do the in order traversal. Right? What is it? It's a binary search tree which has been created by some numbers in that order, right? And then finally we did in order traversal and we got the data in the ascending order. Okay, one of the interesting sorting algorithm which is called tree sort. So these are the results for you to verify, and in order traversal of a binary search tree sorts the numbers. Now let's look into the efficiency, right? Can someone tell me, I mean, okay, before you give me the numbers, what do you think? Is this insertion process of a node in the binary search tree efficient? Or in other way, how should we determine the time complexity of the insertion process of a node in a binary search tree? Could be a question. Yep. Average case. Yeah, that's an interesting suggestion. But in what terms we should describe it, right? In terms of what? Yep.
Log base 2.
Log base 2, interesting suggestion. Yeah. Log n. That will be an ideal situation, right? So guys, again, I was over ambitious, right? I was expecting too much from you people. Guys, for a tree, whenever, oh yeah, go ahead.
I think it depends on whether or not the tree is like balanced. So if the root node is the
Very good, very good, very good observation. This is an information you should know. When we talk about the efficiency of an operation on a tree, we need to describe that in terms of a parameter of a tree. What do you think would be the parameter of a tree which will determine whether the tree looks like balanced or unbalanced? Somebody mentioned balanced and unbalanced, right? We will learn it. We'll learn about that in the next class. Yeah. So depth of a tree, very good. Right? It all depends how deep your tree is, right? 45, 35, 25. Is this a binary search tree? Is this a binary search tree? This is a binary search tree. Look at it. All the nodes on the left hand side are less than 45. 45, this is 35, 25 is less than 35, 5 is less than 25, right? But the depth of this tree is higher, right? So the message is that whenever we evaluate an operation in terms of time complexity for a tree, then we evaluate that in terms of the depth of the tree, right? And if the tree is balanced or full, then yes, it is going to be log of n base 2, where n is number of nodes. But in this case like this, right, it's a degenerated binary search tree, right? It looks like a linear only. So in this case, it is going to be order of n. So the worst case is going to be order of n. The best case is going to be order of n, log of n base 2. Okay? Questions? Yep.
you just say it's O of n where n is the depth?
D. It will be order of D, right? So you should say order of D, where D is the depth of the tree, right? But don't stop there, right? Because if you're saying order of D, that is a shortcut, which is correct, but it's a shortcut, right? You should tell what is the depth going to be, right? So if it is totally balanced, the depth is going to be log of n base 2. Otherwise, it could be in the worst case n as well, order of n also, right? So let's look at this thing. So very, very simple calculations. For a fully binary tree with n nodes, what is its depth, right? So these calculations you can do. Total number of nodes n are going to be 2 to the power 0, which is 1 as the root, then 2 in the second level, then 4 in the third level, so on and so forth. If it is full, yeah, full, right? Good that we have full. If it is full, then at the depth level, at the depth d, we'll have 2 to the power d. Add them up, for which we will need the geometric series summation, Okay, and this boils down to 2 to the power d plus 1 minus 1, which is n. Do simple mathematics and take minus 1 to the left hand side, it will be n plus 1, and then you'll have to take log to the base 2, and which will give you the value of d, which is log of 2n plus 1 minus 1. Okay, which you can simplify as big O of log n if order of complexity is required, but this is the perfect number that we are looking at. Question: can we do this basic math, right? Therefore, an insert operation is going to take big O of log n time for full binary search tree, because we have to examine one node at each level before we find the insertion point, and there are d levels. Okay, that is a beauty of binary search tree. When you have to insert a node at like here, right? If it was 50, you need to add say 70. So you compare with this one, you come here, then you are comparing with this node only, right? At a depth, at a node, we compare only with one node, not with all the nodes. Okay. And guys, I mean, there's one more traversal possible, which probably we will do in the graphs. That is called level order traversal, right? A, then B, C, D, E, F, right? Level by level order traversal. But we don't discuss that here. Okay. Next question. BS trees are all binary search tree is full, right? All the binary search trees are full. Is that a valid statement? No, right? That is not guaranteed. We have that which is not full, right? So no. So if all the BS trees are not full, then we can think of the worst case time complexity also. So as an example, if we are creating the binary search tree from these numbers, so it will become like 11 and then 21, then 39, then 45. You know where we are going, right? So it's all linear. So in that case, when you have to insert, then in the worst case it might take order of n time, right? So be careful about these short questions that look easy. They are in fact easy, but it is very possible. It's possible that you might miss the correct answer. Question? Yep.
Wait, for that example, shouldn't they be on the right because it's greater?
Oh yes, that is a blunder from my part. Thank you so much for correcting. Yeah, you are right. These are less than. Okay, so let me do that exercise because I created a wrong tree, right? 11 and then 21, then 39, 45, 62. You can do it, right? Yeah, sorry about that. That was a total blunder. Good, right? So probably the most difficult code that you're about to see, and probably the most difficult concept that you're about to see. So please pay attention, and you may have to work it out after the lecture also. So don't hesitate in coming back to me, in my office hours or the next lecture. I'll try my best to explain, right? Because remove is complex in binary search tree, which will involve recursion as well. Okay, so let's see how much we can follow. Removing from a binary search tree. So what is the general idea? So the general idea goes like this. We will be given some item that we have to remove, right? So we will search for that thing. Let's say if I'm saying remove 25, so that item should be given to me, right? And I will have to search for that item. Just in case of insert, we were just comparing that item, but here will be given. Somebody will say, okay, fine, remove 25 or remove 50. So we will search, and the process starts from the root itself. Start at the root and search for the item to remove by progressing one level at a time until there are two possibilities. Item is found. If the item is found, we will remove. It is also possible that the item was not present. Right? So that will happen if you reach the leaf and the item is not found. So if the item is not found, what will you do? You can't remove, but you need to tell that we failed in removing, right? So here it makes sense to have the return type for this method as Boolean, right? We will return true when we remove the item, we will return false when we could not remove the item, right? Is it an agreement with something that we have done in some existing classes, right? Array list, if I could vaguely remember, right? If you remove, then in one of the version it would return true or else false. So it is very common, right? So we will follow that approach. If the item is found, we will remove the node and repair the tree so that it is still binary search tree. If I am saying remove 35, right, now we will remove 35 in such a way that it still remains a binary search tree. So as a human being, you'll say, okay, fine, do this, you're done. But when you have to write a program systematically, then that will involve serious thought. Okay, so let's approach this problem by looking at different cases. So there are going to be 3 cases. Pay attention to those, and as I recommended you, weekend coming up, it won't take more than 1.5 hours for binary search tree. Just type out all these things in one class, probably 2 class. One class would be for BT node, the other one would be binary search tree, and play with it. So here we go. Boolean is the return type, it is public, we are calling it remove. This is the item that we want to remove. So before we even start looking at it, now tell me, what is your thought process? How will you remove a node from this tree, right? How many variables you would need, local variables you would need, right? Can you connect it with some remove operations that we learned in one of the earlier data structure? Yeah? Let me give him the chance to do. Yep.
It was removed for inputs. We use a trailing pointer and a null pointer.
Right? We have already learned that. We already know that concept, right? The same we will be using here. Because one of the, see, when I have to remove 35 as an example, then after removing, I would like to connect it to the next node. How to do it? I should have a trailing pointer. See that, right? So the same concept we will be using, the same logic we'll be using. We would make use of a trailing pointer. So here we go. One of the variable is our cursor that we will set as the root, and then pre-PTR, I think we call that previous PTR, but here we will use more meaningful name and we will call it the parent of cursor, right? So the same concept, your parent of cursor will start from here, somewhere null, and your cursor would be the root. Good. Then what we do? Let's start the search, right? And how do we search? Okay, let me not bother you people too much, right? While, let's use a while loop, and we will check for this condition. The cursor should not hit null, right? That is one condition. And what should be the other condition? We are searching for that item, right? As long as we did not find the item, we will keep searching. Is that thing clear? Right? As long as our cursor is not equal to null and we did not find the item, let's keep searching. So the second condition is cursor.getData is not equal to item, right? So these are the two conditions on which we will continue to search, and that's the reason why we have this while loop. And what should we do inside this while loop? Assume that I give you this partially complete program in the exam, fill it up, right? You need to know the sequence, right? Okay, we need to update these things, right? What do we need to update? We need to update cursor and the parent of cursor. But yeah,
Like, don't have to check with like this, it should be something similar than the one where we returned.
Very good. Good. Very good. Guys, we are removing an item from a tree which is binary search tree. It has a property, right? So when we want to remove an item, then we need to intelligently search for that item, right? So this should be intelligent, not like next and a linked list. So as he pointed out, we will check that where exactly this item might be present. Is it present on the left subtree or on the right subtree, right? And according to that, we will make a move. So parent of a cursor is equal to cursor, that we can anyway do, right? Because it was null, let's take it to the root, because anyway we are about to move here or here. If it is 70, we will go to this side, but if it was less than 45, we will go to this side. But in any case, the cursor which was the parent of cursor which was null should be pointed to the cursor, right? So that's the first statement we are doing here. Parent of cursor is equal to cursor. And now here's the condition that we will check. If item is less than cursor dot get data, what we do? Cursor is equal to cursor dot get left. Good. Else, not difficult, right? Done. This will keep you in the loop as long as these two conditions are correct, right? So you will come out of this while loop in two conditions. If your cursor is null and you came out of this loop, what does it mean? Cursor is null. We came out of this loop on the condition that cursor is null. What does it indicate? Yep. Not found. Okay. Guys, this is simple case, right? The last would be extremely challenging. Good with me? Okay, let me show you this example, right? If you still have questions, then we'll go back to the code. That's your binary search tree, right? Yeah, follows all the requirement. And we want to remove the item with the value 74. Okay, so what will happen? Let's trace the program on this example. Parent of cursor is null. Cursor is set to root, which is 45. You want to remove 74. You compare 74 with 45. You figured out that it can't be present on the left hand side, right? This is the left. So you would move to the right hand side, right? So when you're moving to the right hand side, you would push this thing, parent of cursor, to the cursor which is root, and now it has moved to 83. You compare 74 with 83 and you figured out that 74 should be present on the left hand side of 83, right? So you will advance in this way. Fine. And at 62, when you will compare 74 with 62, then 74, if present, should be in the right subtree of 62, right, which is null. Then that means it's not present, right? And you'll come out with the cursor of the value of cursor as null, right? So what should you return in this case? Return false. Yes, false means we failed. Yeah, we failed because that was not present, right? So what's the condition? If cursor is equal to null, we return false. Case number 2. Case 1. Any explanation needed for case 1? Good. That was the simplest one. Case 2 is interesting, right? In case 2, what we have? Item is a root and root has no left child, like 45. What should we do? Sorry? And okay, you are saying we should go to the right, and what to do on the right? We did go to the right. You don't need to go anywhere, right? Just set the root to this one. It's a simple case, right? Kind of treated as a corner case. So else, if cursor is equal to root and cursor dot get left is equal to null, right? So here its left is null, that which is helping us out. Do we have anything on the left hand side of 45? No, and this is what we need to remove, right? Corner case you can treat. So in this case, very, very simple. Our cursor is equal to root, but cursor dot get left is null. This is null. So in this case, we will simply say root is equal to root dot get right. Done. It's gone. So that was the second case. Third case is slightly interesting, which is over here. Okay. Cursor 22, which means we want to remove 22, and 22 is a node which is not root, but it does not have any left child, right? Okay. So what do we do in this condition? In this condition, we will disconnect this node. We can, right, because it does not have any left child, and rather connect 45 directly to 31 as its left child. Got it? In data structure, at some point you will have to think like a research student. Just dive deep into it. Don't worry if it is taking 1 hour, 2 hours, 3 hours, or if even it is taking 1 day, 2 days. If it is taking more than 1 day, definitely you need to see the TA or me. All right, and we will try our best to help you. But it's not as straightforward as was CSC 114. Concepts are deep, right? Okay, and you'll keep forgetting it. There's nothing wrong in it. So these are complex topics, slightly complex. Okay, fine. So in this case, what we will do, we will connect 31 to 45. Case A. Case A is when the item is a non-root, 21, that we want to remove, and does not have a left child, right? Okay, should I ask you another question? Is there a possibility where we can have a root, where we can have a node like 22 that does not have the left child but could be present on the right hand side of 45? Is that possible? Yeah. 67 is also a node which is not root, and its left child is also missing, right? This is one situation and this is one. All right, so in this part of code, first we will look at the situation where the item that we want to remove is sitting on the left hand side of its parent, versus the second picture that I showed you, where this node with this interesting property, who is not root but its left subchild is missing, is in fact the right child of the parent node, right? These things make it really, really complex, guys. Okay, and these are the questions that are asked in the interviews like Google, Amazon, and all are of this complexity, guys, or maybe slightly more complex. Okay, so it's worthwhile. Questions, guys? Good? Can you write it? You with me? So how do we check? Let's start again. Okay, as if cursor is not equal to null. Cursor was null in the previous case, right? So this is in continuation with the code. As if cursor is not equal to null, is not equal to root, and cursor dot get left is null. What you do, if cursor, this is the most important thing, right? Like, how do you check whether this node 22 that you have is on its left hand side or the right hand side, right? For that, you will use this condition: if cursor is equal to parent of cursor dot left child, left, right? If this cursor, which is the reference, is in fact equal to parent of cursor dot get left, right? If, see, how do you check that whether we are the left child or the right child? Okay, fine. Just compare these two references. If cursor is equal to parent of cursor dot get left, then that means we are on the left hand side. Okay, so what you do in that case, you will say parent of cursor dot set left is cursor dot get right. get right. This is cursor, cursor.getRight, that was the reference which you want to assign to the left field of 45. Clear? Was saying you'll have to spend time, right? And you would need a piece of paper, definitely you would need a piece of paper, all right, understanding these things. And otherwise, we'll come to this case where if it is on the right hand side, then you will set this 91 as the right child. In the previous case, you set 31 as the left child of 45, right? Here, you will set 91 as the right child of 45. Got it? So here we go, as parent of cursor dot set right, cursor dot get right. It is still cursor dot get right, but we set that as the parent of cursor dot set left. Here it is parent of cursor dot set right. Got it? All right. So now the most difficult part. Okay, the most difficult part is when you have to remove the item like 45. Okay, and for this part I would say for the time being you should forget about implementation, right, which is intense, involving some deep recursion. Let's conceptually get this point, right, like what is the approach. And it is a kind of trick only, it's a trick. And most of, I don't know whether I should be discussing interview questions, but I discuss just to keep you motivated, right? This is not wastage of your time. Spend time and write the code and save your code for your interview time also. Save it somewhere so that you don't have to do it again. So the trick that is used to remove the item like 45 is, can someone, do you want to think about it? Okay, let me give you the trick, right? What we do is we find the largest value in the left subtree. This is the left subtree, right? What is the largest value of the left subtree? 39. You all agree with me? Right? So we find the largest element of the left subtree, which is 39, and replace 45 with 39. Okay, making sense? We have to remove 45, right? Let's erase that value and put 39. Now the only problem right now we have is duplicate nodes which are not allowed. So what we would do, we'd remove 39. Trick, right? It's a trick. Okay. So I'm saying you may forget, that's all right. Then remove the rightmost node, which is 39, but be careful because 39 may have its child nodes, right? Because of which it gets little recursive. Yep.
Could you achieve this by replacing it with the smallest node, right?
Very good. Yes. 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 That is possible too. Okay. That could be a candidate. So his point is, good. I'm happy that you could think about it, right? What we want is that the tree should remain binary search tree after the removal of that node. We don't want 45. So I said that one of the candidates that could replace 45 is 39. It will still be a binary search tree. And we will fix the tree. We have to fix the trees, right? It's not very straightforward. Ultimately, after this, we will work it out. Okay? So one candidate is 39. The other candidate he's saying is could be 62, right? That's correct, right? In some implementations, people also use the leftmost node of the rightmost tree. Good? Okay, so you need to be very, very careful because when you with 39 you may further have its left child. Can 39 have a right child? Can 39 have a right child? No, if that is the case, it won't be at the rightmost, right? The rightmost is a node that won't have the left child. Okay, so it is possible that it may have the left subchild, and we'll have to fix it, right? Then the recursion gets into play. All right, questions? All right, so let's look at it as cursor.setData. We need to erase the data of 45, right? So cursor.setData is cursor.left get left. Why get left? Because now we are moving to the left subtree, right? We want the rightmost of the left subtree. Good, right? So we will say cursor.get left dot get rightmost data. Now what is this rightmost data? This is a method which we have not seen yet, but this method I'll show you in the next slide. You need to write in the BT node. Okay, so the assignment that I'll have for you people would be, please implement all these things, right? Make one class for BT node, just copy all these methods that we have for BT node, right? And then write all these methods that we have seen till now and play with it. While playing, you will figure out that these things will fall in place. Okay, so what is the purpose of cursor.set data, cursor.get left dot get rightmost data? To get the rightmost data and put that in this node that you want to remove, right? Erasing 45 and putting 39 in our picture. The next is probably the toughest one, which is fixing the tree. And you know, I mean, in the code, if you want to memorize, you should not memorize. If you want to memorize, you are done, right? Because it is very similar. But if you want to reason about it, you'll have to think recursively. So what we have, cursor.setLeft, cursor.getLeft dot remove rightmost. Done, return true, done, done. And here are the two methods which are recursive in nature, which you will have to put in the BT node, right? So what I will do, I will stop right here with highly recommending you to, you know, play with this code, right? And then I'll see you in the next class. We will finish this part, and then I'll take you to yet another extremely interesting binary tree, heaps. All right, thank you so much.